Hi, my name is Nitin, and I would be presenting a survey on swarm robotics. Let us start off by defining what a swarm robotics is. Swarm robotics is a study of how we can design a large number of simple agents with limited computation and communication capabilities, and to study the collective behavior that emerges from these interactions. The inspiration for swarm robotics was derived by observing the social insects. The social insects could perform very complex tasks with very limited individual capability, and they exhibited self-organized behavior even though they had almost no individual capability. Many such behaviors were later on adopted into swarm robotics. The key characteristics which define a swarm robotic system is that they are completely autonomous and they execute any given task parallelly. They also exhibit robustness, which means that in case of a failure in any one robot, another robot can take its place and complete its task. This robotic system is also known to be highly scalable, as in we can add as many robots as we want to as long as they follow the basic rules. The field of swarm robotics is very vast, and there are currently multiple areas of research, mainly in control and coordination, communication, fault tolerance, and task allocation. Each of these fields is explained the most current models. There have been many methods put forward to control the behavior of the swarm, but all of these methods fall into two categories. The first category is a centralized control, wherein a robotic agent acts as a leader which is in the charge of the whole swarm, and it takes the decisions for the swarm. The advantage of this is that an optimal plan is produced for any given situation, but it has more disadvantages as the swarm is heavily dependent on the communication of the leader, and it also has a very sluggish response to the changes in the environment. The second category is distributed control, in which all the agents are completely autonomous. This approach is very advantageous as we can employ a very simple design to tackle a problem, and also they have high amount of redundancy. That is, they are not heavily dependent on one particular type of robot, and also it is easily scalable. But the key and open challenge in this type of approach is the coordination between the robots. Nonetheless, distributed approach forms central in forming self-organized robot structure. In this slide, we have a video on a project conducted by Harvard University which employed self-organization in robots. Now let us explore some of the control methods through which we can control a swarm system. The first method, as shown here, is control using local swarms. In this method, a local swarm is formed within a swarm. A local swarm is defined as a robot with just its neighboring robots. And the control is achieved through virtual forces. There are two types of virtual forces which are applied to the swarm. That is local force, which consists of attraction and repulsion, and which maintains the stability in a swarm, and an advanced force, which is responsible for the swarm to propagate to its goal. So using these virtual forces, stability is maintained in the swarm and it also achieves its goal. The next method is a dynamic leader based swarm control. This is a central control approach in which a leader is leading a swarm. But unlike other control approaches, the leader is dynamically rotated in the swarm. This is done using a random competing clustering algorithm which is used to distribute the leaders as evenly as possible across the swarm. This is advantageous over a static approach as it avoids most of the disadvantages which is faced by the leader based swarm control. That is, a failure in the leader will not cause a failure of a swarm. As it is dynamically rotated, the position of the leader can just be rotated to the next robot. It also provides robustness. Our next method is psychomimetics based control. Psychomimetics is a form of distributed multi-agent control where the agents are treated as a point mass particles and their movement results from the interactions of artificial forces that act on these particles. One can define these agents with different masses, coefficients of friction, and so on, and the combination of these parameters can produce a wide variety of useful behaviors. This can be used to control the swarm in real time, and it is generally divided into two approaches. The first mechanism involves a top-down approach wherein the global swarm characteristics are defined and the parameter setting of individual agents are optimized to achieve such characteristics. And in the second control mechanism, the bottom-up approach that does not modify the behavior of current agents. Instead, virtual agents that do not exist in the environment interact with the real agents via the same force law mechanisms, and they can thereby influence the swarm behavior. Our next method is incremental evolution based control. Evolutionary control is a methodology that uses evolutionary computation to develop controllers for autonomous robots. And incremental evolution is just an extension in which the complex task is subdivided into steps and the steps are divided into various robots. There are four main approaches to the incremental evolution. The first one is a staged approach, in which an objective task is divided into ordered subtasks, each of which is solved by defining an appropriate fitness function. The next is environmental complexification, which is same as staged evolution, but there is a slight difference that the task complexity can be modified. In behavioral decomposition, the robotic controller is divided into subcontrollers and each of which is evolved separately. And lastly, in fitness shaping, the weight sum of multiple evaluation criteria is used to create a fitness gradient so that artificial evolution can follow. Now, let us move on to the next area of research, that is, the communication. The communication in a swarm robot can be divided into two categories. One is implicit, wherein the robots communicate through the environment, and another one is explicit, in which the robots directly pass messages to each other. Now let's see a couple of models in both the cases. Pheromone communication is an implicit communication which was inspired by social ants. Ants used to communicate to each other using a chemical substance known as pheromone. Now, extending on that, virtual pheromone was invented and is used for coordination in the robots. Now, in this virtual pheromone, each robot sends its location to a pheromone server in the form of information packets, and the pheromone server locates the point on its internal map and updates it. The server sends back the intensity of the pheromone to the robot, and since this pheromone map is shared among all the robots, a communication is achieved. The robotic swarm communication network is an explicit type of communication in which the swarms are integrated with a wireless mesh network. The swarm is basically controlled and monitored through central servers, and within a swarm, robots can communicate through a self-organized mobile ad hoc network. A user can monitor the swarm through a PDA and can take immediate action whenever necessary. From this, let's move on to our next area of research, that is fault tolerance. Swarm robotic structures are highly fault tolerant because of their redundancy nature. But still, there can still be faults occurring within the system. Therefore, there are majorly three types of protocols which are implemented to detect such faults. The first one is unsynchronized flashing protocol, wherein each robot periodically switches the LED color that it is illuminating, and whichever robot which doesn't switch is recognized as a faulty one. The next is the ping pong protocol, in which each robot sends out a message ping to which the neighboring robot responds with a pong, and if a robot doesn't respond, it is detected as faulty. The last one is synchronized flashing protocol, in which all the robots flash simultaneously, and whichever robot doesn't is recognized as a faulty one, and this is found to be the most advantageous of all. Our next area of research is task allocation. Task allocation is a means of assigning tasks among the robots in a swarm in an effective and productive manner. The issue in task allocation is to select the best robot to execute the task. There can also be physical interference effect when tasks are being assigned to multiple robots, which means that two or more robots can reach at the same place at the same time. One solution for this would be to have a central manager to coordinate all the tasks in a robot. To conclude, in this survey we have explored various key research areas in swarm robotics and discussed the current models in each of these areas. I have found that the key challenges were in the areas of synchronization and self-organization. These are open issues which are inhibiting the growth of the swarm robotics. Another interesting point I have observed is that none of the methods can be implemented in the real world. Therefore, I believe that the future research should concentrate on solving the current bottlenecks and implementing swarm robotics in real-world scenarios. Thank you.